What's up, guys? It's me, Sir Ernest, and I'm here to solve an example related to the equation of motion in a central force field. Okay, so the problem reads, a particle moving in a central field describes the spiral orbit like this, where R naught is a constant, K is also a constant. Show that the force law is inverse cube and that theta varies logarithmically with time. Okay, so from our definition U, which is 1 over R, this is equal to 1 over R naught e to the negative k theta. Okay, so this follows that the derivative with respect to theta is equal to negative k over R naught e to the negative k theta. And second derivative with respect to theta is equal to k squared over R naught e to the negative k theta, which is basically k squared u, because e to the negative k theta over R naught is u. So, simple. The equation of motion becomes, which is defined as second derivative of u with respect to theta plus u equals k squared u plus u, and this is equal to negative 1 over ml squared u squared f to the u minus 1, or f 1 over u. So therefore, f 1 over u is equal to negative ml squared times k squared plus 1 u cube. So that the force function, so function of R, is equal to negative ml squared k plus 1 all over R cube. So here we showed that F varies with 1 over R cube, which is an inverse cube. Now, conservation of angular momentum will lead us to that function of theta as a function of time. So from conservation of angular momentum, we have L, which is equal to R squared over theta. Okay, so this means that the derivative of theta with respect to time is equal to L over R squared, and this is equal to L over R naught squared times e to the negative 2 kt. So this can be rewritten in integral form as follows. So this is the integral of e to the 2k theta d theta equals integral of L over R naught squared dt. Okay, so here we're not going to set our boundary condition, but instead we're going to use an integration constant, and then later, if we know the initial conditions or boundary conditions of the problem, we can actually solve for that integration constant. But in the meantime, let's set that aside first. So this can now be rewritten as 1 over 2k e to the 2k theta, and this is equal to LT over R naught squared plus c. So again, c is our integration constant. So therefore, from here, we can, the equation of motion in theta as a function of time, manipulating this, we have, so this is, I'm multiplying both sides with 2k, so this is e to the 2k theta equals 2k lt over r naught squared plus 2kc. And then taking the natural logarithm of both sides, that's 2k theta equals natural logarithm of 2k lt over r naught squared plus 2kc. Okay, so therefore, the equation of motion, theta as a function of time, is now equal to 1 over 2k times ln of, I mentioned that's 2k lt over r naught squared plus 2kc. So as you will notice that this shows that theta varies logarithmically with time. Okay, so easy, fantastic. So this ends our solution to this specific problem. So thank you for watching, and then I'll see you again in the next video. Bye bye.